Welcome to This Explainer. Today, we're diving headfirst into one of the most mind-bending, reality-altering topics in modern science, quantum mechanics. But look, we aren't just going to sit here and talk about dry equations. We're actually going to peek at the very fabric of reality itself and investigate a mystery so profound that the greatest minds in physics are literally still arguing about it a whole century later.
So imagine flipping a coin. In our everyday, classical world, when that coin finally lands, it's either heads or tails, right? Pretty simple. But what if I told you that in the quantum world, while that coin is spinning in the air, it is somehow both heads and tails at the exact same time? It's not just a blur. It physically exists in both states until you force it to stop and look at it. This isn't some crazy science fiction. This is the actual reality of subatomic particles, straight from Microsoft Quantum's research.
And you know, this really brings to mind a famous quote from the legendary physicist Richard Feynman. When he was talking about this bizarre dual behavior, he said, "We choose to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way. In reality, it contains the only mystery." So the big question for us today is, how do the different interpretations of quantum mechanics actually explain this singular central mystery?
Okay, here's our roadmap for today. We'll start with the ultimate quantum mystery and the measurement problem itself. Then we'll cross-examine three major suspects: Copenhagen, many worlds, and pilot wave, before wrapping things up by looking at quantum reality on a macro scale.
All right, let's jump into section 1, the ultimate quantum mystery, defining superposition. Now, take a look at the sheer density of the math up on your screen. You've got the Schrödinger equation, Dirac's-Braun-Ket notation, complex state vectors. Yeah, it's a lot. It looks completely daunting. But honestly, I promise you don't need a PhD in mathematics to grasp what's fundamentally going on here. We can actually distill all of this hardcore head-scratching physics down to one incredibly crucial concept. And that concept is superposition. Basically, this is a state where a quantum system exists as a probabilistic blend of multiple potential outcomes all at the same time. Remember our spinning coin? That is superposition in a nutshell. The math on the previous slide perfectly describes that spinning coin. And the wild part? The math works flawlessly, just as long as you don't actually look at the coin. Which brings us to section 2, the measurement problem, the core conflict. If theoretical physics is a crime scene, well, this is the chalk outline. Here is the deeply frustrating paradox that scientists are dealing with. When we aren't looking, quantum systems evolve smoothly and predictably as waves, governed deterministically by that Schrödinger equation we saw earlier. But the very second we observe or measure them, that smooth evolution violently breaks down. The wave just randomly collapses into a single, definite particle state. Why on earth should the mere act of us looking at a particle force reality to make a choice? You've probably heard of the thought experiment that brilliantly illustrates how absurd this all is: Schrödinger's cat. Erwin Schrödinger proposed this back in 1935 to show what happens if you scale this quantum weirdness up. You put a cat in a sealed box with a radioactive atom that has a 50-50 chance of decaying and releasing poison. Because the atom is in a superposition of decayed and not decayed, the math literally suggests the cat is simultaneously dead and alive until you open the box to look. So how do we solve this puzzle? Let's bring in our first suspect in section 3. The Copenhagen interpretation, the observer effect. Developed in the 1920s by Niels Bohr and Werner Heisenberg, this is basically the standard playbook most physicists use. Copenhagen states that particles truly do exist in superposition until they are measured. It is the literal physical act of measurement that forces the wave function to collapse. So the takeaway here is that before observation, quantum objects simply don't have definite properties. It kind of makes you wonder, is reality basically constructed by the observer? Now, looking at Adib Kabir's comparative analysis, Copenhagen has some massive strengths. I mean, it perfectly matches our empirical data and lets scientists make incredibly accurate predictions. But the criticisms are definitely heavy. It's philosophically vague. It implies this sort of mysticism where the universe actually relies on human consciousness, or at least measurement devices, to physically exist. It doesn't tell us how the collapse happens, it just says it does. If that feels a bit too mystical for you, let's move to section 4, the many worlds multiverse, the branching universe. Physicist Hugh Everett offered a pretty radical alternative to Copenhagen in 1957. Many worlds offers this stunningly simple mathematical solution. What if the wave function never collapses at all? Instead, every single possible outcome of a quantum measurement actually physically happens. How? By the universe constantly branching out into a vast, ever-expanding multiverse. The math stays perfectly clean and pure, but obviously the implications for our reality are just staggering. Let's look at how this plays out on a timeline. Step 1. You open the box to check on Schrödinger's cat. Step 2, in universe A, you observe a live cat. But in step 3, at that exact same moment, the universe branches, and in universe B, a parallel version of you observes a dead cat. Both of these realities are equally real, but they instantly become disconnected from each other and can never interact again. When we impartially weigh many worlds, its biggest strength is for sure its immense mathematical elegance. It gets rid of that mystical observer stuff entirely. But the trade-off? Well, critics call it metaphysically extravagant. It asks us to believe in an infinite number of parallel universes that we can never test, observe, or verify. So we solve the measurement problem, but we do it by multiplying reality by infinity. Okay, so what if we want the math to make sense, but we don't want to spawn infinite universes every time we flip a coin? Enter our third suspect in section 5, pilot wave theory, hidden determinism.
Pilot wave, or Bohmian mechanics, tries to bring classical common sense back to physics. It argues that particles actually always have a definite position, even when we aren't looking. The coin was always heads. But these particles are surf riding on a hidden guiding wave. According to this theory, the apparent randomness we see in quantum mechanics, that's just an illusion caused by our incomplete knowledge of these hidden forces.
The major strength here is a big one. It restores deterministic reality. The universe behaves logically again. But the criticisms are severe. To make the math actually work, pilot wave relies on these hidden variables that we can't see, which definitely violates Occam's razor. Worse than that, it requires what's called non-locality, meaning this guiding wave has to influence particles instantaneously across the universe, which directly clashes with Einstein's theory of relativity. All right, let's take all this theoretical debate and see what happens when we bring it into the real world. Section 6, quantum macro reality, scaling up weirdness. You know, it's really easy to just dismiss quantum weirdness as something that only happens to tiny, invisible subatomic particles. But recent breakthroughs are completely changing that narrative. Researchers in Vienna successfully placed an entire macroscopic metal cluster, something approaching the scale of everyday matter, into a Schrödinger cat state. They proved that a large lump of metal can effectively be here and not here at the exact same time. They hit a record-breaking macroscopicity value of 15.5. Now, that number might not mean much on its own, but trust me, it represents a scale an entire order of magnitude beyond what previous experiments worldwide have achieved. It's concrete proof that the measurement problem isn't just some micro issue anymore. It is scaling up into our tangible everyday world. To really put the precision of this experiment into perspective, if you wanted to achieve this exact same level of quantum superposition testing using just a single electron, you'd have to perfectly preserve that electron's state for nearly 100 million years. Literally, and these researchers did it with metallic nanoparticles in 1/100th of a second. They are actively forcing the quantum world into the macro world. Which leaves us with a pretty staggering final thought. If the Copenhagen interpretation is right, and macroscopic objects can exist in superpositions that only collapse into reality when they're observed, then who or what is observing the universe to keep it real? Does reality inherently require a conscious mind? Or, as some theory suggests, does the environment itself act as the observer? The measurement problem remains the ultimate locked room mystery of physics. It's definitely something to chew on, keep questioning, and we'll see you in the next explainer.